Now, I say in the slide deck here that this is efficient pricing. So a blob is built up of smaller chunks. So, for example, if you were uploading a 100 gigabyte blob, then you wouldn't do it in one HTTP post request. You would do it in chunks of probably 4 megabytes. And so there's this, the granularity there is the granularity of the price difference. So if you have a blob that has, say, 100 of these chunks in it, and the change delta was only in 2 of the chunks, then you would only pay for the pricing difference in those 2 chunks. So since for example, I just made 2 replicas of this that are identical because I didn't actually make any changes to them, then I shouldn't be paying anything extra for these because there are no differences. Now, if I changed something within it and then uploaded it, again, I would, and I only changed one of the 4K chunks, say, I would just pay the cost of the original plus whatever the cost is for 4 megabytes for a month. That's what I mean by efficient pricing. Now, another cool use for blobs, and this is the final thing that on the list of things that most people, many developers may not know about Azure Blobs, is you can use it for a semaphore, where I think we can let Google tell us what a semaphore is. Whoops. That's interesting. So, well, anyway, a semaphore is, you may be familiar with the concept of a semaphore flag. It's a flag that you can use for signaling from one place to another. And in code terms, programming terms, a semaphore is often a technique for coordinating work across 2 processes that wouldn't otherwise know how to interact. So you don't want them stomping on each other. So you put a flag in the middle that one of the processes can hold up and say, I want to do this, or I've done this, and now you can go ahead, and they lower the flag, that kind of thing. And one of the kinds of semaphores is a counting semaphore. So this is a snippet of code, this blob semaphore, that I've used to coordinate a very simple task, which is I have many instances of a process running in the cloud. That's easy to do. And I want them to each have or each generate a unique identification number for some of the work that they're creating. So in this case, this particular snippet is dealing with a job ID. And there are various ways of doing that. And this blob approach that I'm showing you here is one way. What this is doing is it's got a well-known blob in memory. It's got a specific blob that's well-known to 2 parties or n parties. And whenever one of the parties wishes to get the next job ID, they want to get the next number, and they don't want anybody else to have a duplicate number, they lock the well-known blob. They grab its contents, and it contains the number 123, say, and they increment it to 124, and they write it back. And Blob has nice support for this in its leasing functionality here that I've just highlighted on screen. And this leasing functionality says, I would like exclusive access to this. And so if any of the other processes attempt to create a lease during the time where I've leased it, they should be put on hold. And this is the basic easy cross-process way in the cloud of achieving this. This lease is a very handy feature. So let me look at the code. Let's look at the code here together. So you need to initialize it at some point. This basically just uploads the number 0 or something into a blob. Call that once. And then forever, for the rest of the time, you call get me a unique job ID. And probably some of this boilerplate stuff you don't really need if this is being called repeatedly. But this is standard stuff that you see frequently, that to make sure that the container and the blob exist, and could create them if they don't. But in our case, it will always exist. So we pretty much start here. It's creating a random time interval. Time before retries is now, that's the starting time before we did any retries. That's for, I believe, just for logging purposes. And then we've initialized our lease to null, and we're going to retry up to 100 times and up to 2 minutes. And we'll try to just, this is a straightforward SDK call with a REST call behind the scenes. And the default is 60 seconds. Give us a lease, acquire the lease. And if it doesn't work, we catch it. We do some sleeping, some fancy stuff here to make sure we're not beating on the thing if somebody else has it, because it might take them a couple of seconds to finish with it. And then we just keep retrying here. If we've acquired the lease, then we increment the string to the next one. There's a string in the blob that we're treating as an int in this case. We increment it and we write it back. If we want to keep it as plain text, the content type, every time you write the value, you're overwriting also some of the metadata. So if you want to keep the content type consistent, you may want to write it every time and set the properties. Then you release the lease when you're done, and then you've got your job ID. And you return that to the rest of your code to keep going. So this is not necessarily a super fast, scalable way to do it. Like if you had many jobs who needed thousands of these per second, this probably wouldn't be a very good approach. This is better for the occasional coordination task. And in this particular case, this code was serving a use case where there were high-level jobs being created, and these jobs would take about 30 minutes to run, and they came in. Sometimes a few in a second would be a lot, so it was kind of low, but a pretty robust way to do it, because you have this nice semaphore that you can use across processes, even across data centers. Pretty flexible in that regard. All right. Safe and secure. So this is nothing super crazy complex here, but just a little bit of a reminder. So we have keys to guard a security account, a storage account, and let's take a quick peek back at those. So these were these. We have two. We have a primary access key and a secondary access key. And you have two, and if you're programmatically accessing blob storage, you need one or the other. And from a functional point of view, they are equivalent. There's nothing that you can do with the primary access key that you cannot do with the secondary access key, and vice versa. You have two, which allows you to do a more managed update of these keys. So if I have code that is using one of these, and it's tying my security policies, or there's some event that causes me to want to modify the key, then I can do so first. I can regenerate one of the keys, and then I can come back to it and come back to the. So suppose my code is using the primary access key. I can first replace it with the secondary key. Then I can go recycle the primary access key, or I can give some of these to some customers and some not, and some to others, knowing that I'm going to want to invalidate it. But if you're sharing this with customers, there's actually a much better way that we're going to look at in a minute with the valet key pattern. But just saying it out there, these are just putting it out there. These are cryptographic keys that the platform has created on your behalf. You should treat them as very important data to protect, similar to database connection string, username, password kind of stuff, because access to these gives somebody complete and unfettered access to everything in that particular storage account. Also like to point out HTTP and HTTPS. So all the API calls that you make against storage, they can travel over HTTP or HTTPS. It's your call, literally. Either one works fine. If you're passing, if in the valet key pattern, as you'll see, you're almost always going to want to pass pass things with HTTPS, because the availability of just access to a HTTP URL is decisive. With a valet key pattern, you won't need the storage credentials that we just looked at in order to do damage.